Alright, our third video in this series, we're going to go over the chain rule and the power rule. Chain rule we're just going to touch on briefly, but the power rule we're going to go over completely. Normally, you go over the power rule and then logarithmic derivatives, but it's actually easier to prove the power rule, and I want to prove it before we go into examples. It's easier to prove it with the derivative of the logarithm. So that's why that was in the first video. So first, let's go over what we're going to prove. What we're going to prove is the derivative of x to a power n being a variable, could be like 2, 3, whatever, is going to equal n times x to the n minus 1. So the derivative with respect to x, that's what this means right here. Derivative of a function x to the n power will always equal n times x to the n minus 1. But let's prove that real quick. So let's just define a function, y equals x to the n. And remember, this is the equation, like the equal sign right here. Don't forget about that. That means whatever we do to one side, we have to do to the other. And as long as we do that, will remain equal, so we can. So what we're going to do is logarithmic differentiation, which is just a lot of syllables for something fancy that's pretty simple. So first, let's take ln of both sides. If we do it to one side, then we can do it to the other. So ln of y equals ln of x to the n. And remember that we have ln of a to the b, then that equals ln of just a times the constant b. That's just one of our rules. So if we move back over here and do that right there, right here, if we do ln of y equals n times ln of x, we're starting to get somewhere, but I mean, you're probably still confused. So now, just like we did to find the natural log of each side, we're actually going to find the derivative of each side. Just like multiplying each side, dividing each side, finding the logarithm of each side. Those are all like functions that we can do. As long as we do it to both sides, it will remain equal. Same thing with the derivative. So as long as we derive both sides, the function will be equal, so we can actually do that. And this extra step of deriving is actually going to ironically simplify this for us. So the derivative of this, we're going to derive both sides, but one thing that we're going to go over real quick, just a quick segue, is the chain rule. And if you have a function f of, say, g of x, then the derivative is going to equal f prime of g of x times g prime of x, where the derivative of this with the inside untouched is going to equal multiplied by the derivative inside. That was ugly. Let me explain. So if we have, say, f of y and we want to derive it with respect to x, well, first we get this y right here is just g of x. All these parentheses makes it look complicated, but we can have f prime of y times, well, g prime, which is just y prime. And, well, it's just the chain rule. What's inside, if you derive it, also needs to come out on the outside. So we end up just getting, I guess that was a bad example, because we get just 1 times 1. Anyways, we're going to touch on that a little later. Actually, right now. So, the derivative of ln of y with respect to x, remember that whatever derivatives on the inside, we get just on the bottom. We learned that in our last video. But we also have the chain rule right here. So right here, first, with the chain rule, if we derive d dx, the derivative of just x equals 1. So if we took the derivative of f of x, it would just be f prime of x times 1. Like, the derivative of the inside is just 1. Which is why I didn't touch on it earlier. It just simplifies, but in this case it doesn't. It will make more sense later. But we need to also multiply by the derivative of the inside in this instance. And because it's not with respect to y, but rather respect to x, it doesn't just simplify to 1. It's actually going to turn out to be dy dx. Now, if it was x with the derivative with respect to x, it actually just end up canceling and we get 1. But in this case, we just get dy dx, which just is the derivative of y. So let's just erase that real quick. So then we take the derivative of the other side, and ln of x, and this will actually just be, if we take the derivative of ln of x with respect to x, we just get 1 over x. And we just ignore the n right here because it's not with respect to x. There's a little bit of addition rule here, but we're going to touch on that later. But in general, it's just going to be n times 1 over x. So how does that help us? Well, if we rewrite this, remember x equals x to the n. So we have y prime over y equals n over x. N times 1 over x is just n to the x. And if we multiply y over, we get ny over x equals y prime. And well, we know y equals x to the n, so let's plug that back in, and we're almost done with our proof. We have y prime, the derivative of y, equals n times x to the n over x. Now, when you have something in the bottom, like say x cubed over x squared, this can just equal x3 minus 2. Powers in the denominator are just negatives, and you can add those powers up and you just get x. Like that will just equal x. So that's what we're going to do here. This x to the 1, we can just do x to the n minus 1. Multiply that by n because we still have that here. So y prime equals n times x to the n minus 1, which is what we have right here. But let me just rewrite this a little better, because it got a little cramped towards the end. So y prime, which another way to write it is just dy dx equals, when y equals x to the n, is just going to be n times x to the n minus 1. That's our definition. So that's our power rule. And notice how just multiplying the front and then subtracting 1 power is way easier than your whole f of x plus delta x minus f of x all over delta x, and then you find the limit. It sucks, and it's too much work. So we're going to be doing this shortcut for a while now. And we still have some time left, so let's just do some examples. So in this case, let's say y equals x squared. We did this in video 1. And well, does the power rule apply? Well, our n right here is 2. So we multiply the 2 out in front and we subtract 1. So we end up getting 2 times x to the first power. And x to the first power is just x. So we get 2x. And verified in our first video, the derivative of x squared does equal 2x. Let's try another one. Y equals 4x to the 5th. Well, if we multiply the 5 out in front and then subtract 1 power, then we get 4 times 5 times x to the 5 minus 1 equals 20x to the 4th. And that will be the derivative of 4x to the 5th. You can start to see how fast this can get. Let's just do y equals 3. You may be wondering, well, there's no x in here. Well, what we can do is multiply this by 1. This is also a quick little proof. We can multiply this by 1, and anything to the 0th power is 1. So we can multiply by x to the 0. And, well, if we bring out the 0 in front, 0 times 3 times x to the negative 1, well, because it's multiplied by 0, it's just 0. So that's our quick little proof of any function, like any derivative of a constant term 3 is just going to equal 0. And that's all the time we have.